Hello, this is Helen Park, an undergraduate research assistant at TTM Lab, Teng University. Today, I'm going to review a paper named Enhancing Semantic Text Similarity with Functional Semantic Knowledge in Patents. The table of contents is as follows. This is bibliographic information section. This paper was published in the Journal of Informetrics in 2024, and the keywords are semantic text similarity, subject action object, functional semantic knowledge, PI LSTM, patent similarity, and pre-trained embedding. Introduction. Capturing patent semantic similarity is one of the fundamental needs because it enables efficient extraction of technical information, detection of infringement risks, and assessment of novelty and innovation of patents. In the early stage of literature, patent similarity evaluation methods were categorized into several classifications using IPC codes, bibliographic analysis, and lexical-based approaches. Content similarity is determined through string-based, vector-based, and knowledge-based method. Recently, the SAO structure, which has emerged to represent technical solutions themselves, has been instrumental in aiding the semantic understanding of patents. The SAO-based method has the following challenges. First, limitation of SAO-based methodology. Most SAO extraction algorithms heavily rely on domain-specific vocabularies and syntax models. SAO processing involves the problem of semantic uncertainty. Due to the complexity of SAO triples themselves, their impact on subsequent similarity calculation is limited. Second, structural issues in patent similarity calculation. Non-functional relationships in patents are disregarded by the SAO structure. There is insufficient extraction of entity sequence, which include fine-grained semantic relationships. Third, lack of benchmark datasets. There is shortage of dataset evaluating patent text similarity, STS. Existing datasets do not adequately reflect the characteristic of specific domain or text. Additional evaluation metrics such as rank-based datasets are needed. Related works. Semantic algorithms for patents are as follows: manual classification system, citation analysis, semantic analysis, keyword analysis, SAO-based mining, and patent feature-based network. You're probably already on top of this, so I'll move on. And additional approaches are SAO-TRM method, traits-based knowledge utilization, and design-oriented functional model. Similarity tests can be categorized into following four types. First one is paraphrase identification. Second one is semantic textual similarity. Third one is natural language inference. And the fourth one is question answering. And also lexical-based algorithms, vector-based approaches, knowledge-based similarity are in current research approaches for determining text similarity, like n-gram, longest common substring, dice coefficient, and Joker similarity are in lexical-based algorithm. Machine learning-based method that use vector represents of text are in vector space approaches. And latent semantic indexing and latent Dirichlet allocation are also in knowledge-based similarity. There are several approaches in deep semantic matching. With the introduction of pre-trained embeddings, dense vector analysis of patent has become feasible with DNN architecture. There is a sham-based method. it is operated by comparing two input data points. It is divided into two models. The first one is initial model called TSSM, and it is composed of a simple, intuitive bilateral encoded architecture. Second one is later model, and it is combination with word hash and CNN structure. There is also interaction-based model, advanced model, and semantic textual similarity (STS). Let's move on to method and models. The main challenge of patent semantic similarity research is the lack of semantic similarity corpus. So the author collected data in PTAB, patent trial and appeal board, and got patent pairs in independent patent. Using patent matching data and ranking data, experts evaluated compare the ranking of patents. For patent pairs, the similarity between two patents is evaluated on scale to 0 to 3, while for individual patent, for ranking of a specific patent in a research result in asserted. The existing SAO-based method have low accuracy and high semantic uncertainty. Current patent ontologies lack fundamental and non-fundamental combination and attribute information, limiting semantic analysis. Therefore, the following approaches are proposed. First, decompose patent content into technical solutions to derive key features and relationships, forming a functional hierarchy. Second, utilize the FOP structure, which analyzes and represents the functional semantic of patent in detail. Third, perform labeling and classification through named entity recognition NER and relation extraction RE. So the graphic below is a simple graphical view of functional semantic knowledge of a patent called FOP. Data preprocessing is performed by removing unnecessary information. FOP was performed with BERT by LSTM and CRF model. FOP is composed with function, object, and property. Function indicates actions, operate, and effect. Object indicates the material, state, and entity on which the technology operates. Property indicates the characteristic and parameters of the object. The graphic in below stands for schematic diagram of by LSTM and CRF model structure. Utilize FOM data, convert FOM into vector, and they performed similarity calculation. There are vocabulary-based and vector-based methods for distinct similarity calculation. Jockard index and inclusion index are in vocabulary-based method, and cosine similarity, Pearson coefficient, Spearman coefficient, and knowledge-based method are vector-based method. Calculate similarity between text using a deep learning-based matching model. Utilize deep learning or effectively learn the complex meaning of input text by utilizing TNN, CNN, by LSTM, attention mechanism, etc. Result and discussions. For getting direct similarity calculation result, a weighting strategy that places greater emphasis on key technical features can enhance the performance of patent data analysis. Word embedding techniques such as globe model can be utilized as well. And for getting deep matching calculation results, they make an evaluation and divide it into training, validation, and test data in a ratio of 6 to 3 to 2. Finally, they got the discussions and remarks. The attention mechanism is a way to allocate weights, which is effective in processing more interaction features and implementing local and global mapping, even with limited computing source. Second, when comparing the two types of FOP, spliced vector and average vector, the average vector method outperforms the spliced vector method. This is because dense vector representation is more effective in feature learning in the universal semantic space. This framework focuses on three key aspects. First one is a method to extract flexibility organized detail types of patent knowledge. The framework includes methods to extract detail types of patent knowledge, such as FOP combinations, and organize them flexibly to improve the analysis process. Second one is a method to utilize word expansion tools and IPC codes to enhance the breadth of analysis. Word expansion tools and international patent classification IPC codes are utilized. These tools help identify border connections and meaning within patent documents. Third one is a method to assign higher weights to the key features of patent segments. To prioritize important sections of patent documents, this framework assigns higher weights to the key features of segments. This ensures that the most critical parts have a stronger influence on similar calculation. Let's move on to case studies. Now this is case studies. They conducted searches based on a global patent database to evaluate how well a search system can identify a specific patent or target patent is predetermined, and each method is used to search for a target patent to determine its position in search result list. Similarity calculation were performed by comparing the FOP and SAO structure. It was observed that FOP-based method achieved higher rankings in top N at 100. In advanced experience, deep learning models, validation was conducted with using interaction-based models, and integrating average FOP represents into deep models improved search rankings. Now this is conclusions. In conclusion, this study proposes the use of FOP enhanced semantic text similarity in patents. Instead of relying on traditional SAO structure, FOP was introduced to strengthen semantic text similarity analysis. To achieve this, STS dataset was prepared, including both matching and ranking datasets. Through a comparative analysis of lexical-based, vector-based, and knowledge-based method, it was found that the FOP-based approaches outperforms others in semantic matching performance. Furthermore, the integration of classification information such as IPC code showed potential for improving search performance. The importance of weighting key patent features was also needed. In conclusion, future research can focus on improving FOP and SAO extraction techniques to enhance performance. Additionally, expanding deep learning research could provide more advanced methods for semantic analysis. Leveraging pre-trained model like BERT and GPT offers a promising way to strengthen sentence-level understanding for patent text. Finally, developing diverse representation learning algorithm could broaden capabilities and open up new probabilities for semantic text analysis. This is end of my presentation. Thank you for listening.